Continuing along, let's get into this hybridization thing. So once again, I hope that this is more familiar stuff to you, but also I hope that I'm able to add some things that you didn't know before, okay? So let's do it. So the first hybrid orbital we're going to talk about is sp3, okay? And so here I've got my classic general chemistry notes up, right? We know from atomic carbon, it's a 2s2, 2p2, okay? And so we kind of, this is often viewed as a promotion and then a hybridization, okay? Although it's not quite really like it's promoting to an excited state, even though delta L is allowed to be plus or minus 1, that's fully allowed, right? For example, this 2s can shift up to the 2p. But again, it's not really like an excited state, like, pumping energy into something and watching it promote to an excited state, okay? What this really is truly what we call hybridizing. And I'll get into what is that more specifically meaning, okay? But in any event, if we kind of view this like this promote and then hybridize, our 2s2 gets promoted to this 2p3, and now we have 4 unpaired electrons, 1 in each px, py, pz, and 1 in 2s, as indicated as such, okay? And we view this as creating what's called a new orbital, a hybrid orbital, which is sp3. And it's literally because there's 1 s and 3 p's, okay? And so that kind of looks pictorially like something like this, where we can see an overlap of our s orbital with our p orbitals. And because of the confluence of constructive and destructive interference, right? Remember, there's positive regions, so there's the positive z, the positive x, and the positive y. We also know that there's negative regions. There's the negative x, the negative z, and the negative y. And so all of those various regions will interfere constructively and destructively to result in this new hybrid orbital shape that we all know and love as the sp3 with the 109.5 degree tetrahedron bonding arrangement. Okay, so hopefully that is what you remember, the review. But now, if we look at the new stuff, how we actually construct this through the process of quantum mechanics, that's right, hybrid orbitals are superpositions of atomic orbitals. And so this gets to be pretty intense. So let's put this all together. And so I'll remind you, right, our ket means wave function, right, just as a friendly reminder, okay? And here, so there's 4 new wave functions we're going to create, the H1, H2, H3, H4, and I've put this little vector notation right there to indicate that each one of these wave functions do end up with a direction-specific orientation. So for example, if I look at the H1 wave function, the H1 wave function is itself a superposition of 2s, 2px, 2py, and 2pz. So remember, each one of these would be the full wave function. And later on, coming up, I'm going to show you how we dissect all these wave functions, okay? And if we were to now look at then the magnitude, and not only I shouldn't say the magnitude, but the sign, right? We've created this superposition with all positive elements and our basis set. If we were to now graph this in our XYZ coordinate system, right? The positive px, the positive py, and the positive pz, and of course we know 2s has regions of positive and negative because it's spherically symmetrical about the origin, then what we would get is this H1 going into this positive coordinate region, right? So it's going to be all positive. Positive x, positive y, positive z. Okay? Well, what about H2? Well, now H2, we create negative elements in the px and the py, and still a positive element in the pz. And all of that order is just switched around in H3 and H4 to give us positive and negative permutations of each. And of course, we will need 2 of each, right? So if I look at px, I have 2 positive instances of 2px, and I have 2 negative instances of 2px. And same with 2py, and same with 2pz. Okay? And I don't need to do that with 2s, because remember, s is spherically symmetrical about the whole coordinate system. And so now if I were to look at that and draw those up, right, assuming I can draw this on this reasonable scale, I would now have still into the positive z, but now into the negative y and the negative x. So I'm going to draw that looking something like that, going back into that coordinate. And of course, if I did H3, now that's going to be into the negative z and the negative x, but in the positive y. And so that's going to look, let's see, something like that, right? It's going to go out into that direction. And then now, of course, the H4, the positive x and the negative y and the negative z, so that's going to make it go out something like that. So my shape looks really terrible. But all of those directions that I'm showing you, all of those vectors, would then have an angle of 109.5 between them, which is pretty cool, okay? And then so now when I take all of these basis sets and add them together, I now get the SP3 wave function. And what do you know? Look what I have right here to the right of me on Mathematica. So I know the font on this is kind of small. So actually, let's just go ahead and turn it up for just 1 second so that you can see it. So there we go, right? I've got that exact. So I'm not showing you the equations yet. We'll get there, okay? And I've also put this in an x, y, z coordinate system, which I'll describe in a minute. And I've done the x, y, z coordinate system for convenience so that I can get those directions. I can get those appropriate vectors, okay? And so now what's pretty cool is when I've got the, right, the SP3, I've got the linear sum of all of those. I've got the SP32, which is really to say like the H1, the H2, the H3, and the H4, right? All those different permutations. And then now I plot the sum of them. So I'm plotting them all, I should really say I'm plotting them all individually, okay? I'm not adding them together, but we know that the SP3 will be a superposition of all. But for best visual representation, if you look at them all individually, then we get something like this, which is pretty cool. And I haven't done, you know, I haven't measured the angle between these, but it's 109.5, okay. And what's also really cool is I'm seeing the negative regions of the wave function, which I've colored in red, and I'm seeing the positive regions of the wave function, which I've colored in green, to really show you that importance of the positive and negative regions, because that's what shows us all in those different directions. So this is pretty cool stuff, okay? So I'm going to make that a little bit smaller so I can shimmy that over a little bit. Okay, so moving along.